Hello and welcome back to Calculus 3. We are starting chapter 14 on vector valued functions, vector calculus. We have a way to describe a straight line in 3D. So the line, not sure why this is red, but now there we go. L in a three-dimensional system was described as x equals x0 plus at, y equal y0 plus bt, z equals z0 plus ct. So these are the three. And as you can see immediately, you have each variable to be on its own. So 3 dimensions, 3 variables, all controlled by the same parameter t in time, so that if there is a bug over here, this bug might be at t equals 0 here, then it walks over to t equals to 1 second here, t equals 2 seconds here, and so on. So you see that the position along the line, right, where the bug is, depends on the time. Now, what we called this earlier was set of parametric equations. Today, we are learning something is called a vector valued function. So we are going to take this and put in the single vector r of t. It's going to be a row vector of x0 plus at, y0 plus bt, and z0 plus ct, and we will call this a vector valued function, and this case is three-dimensional. Obviously you can have this in any dimension. We will start with the 2D cases first and then do the 3D, but again, this is something that works for n-dimensional space. So every single dimension you can think of would have a function, a vector valued function in there. So to start, we take any set of parametric equations and we just stuff them in a vector. So it's just a different representation of what the vector value, of what the parametric set is. So now, to describe this a little bit better, we are going to give it like a formula or whatever. We can call this x of t, y of t, z of t. You can also put, if you want, f of t, g of t, h of t. So whatever notation you want to use. Now I like the x, y, and z because we get to compute and understand it better. So let me just box this real quick and write that this over here is vector valued function. Vector valued function. Now let's say that you have a vector valued function given as, so it's in terms of t, let's say 3t squared, 1 minus t, and 1 over t plus 1, for instance. So from this vector valued function, we see that t is not allowed to be a negative 1 because that would make the third component, right, invalid. But other than negative 1, everything else is okay. So now, why is this called a vector valued function? Because at t equal to 0, let's say, you can calculate r at 0, which is going to be 0, 1, 1. So for the time input of 0, you get a vector 0, 1, 1, which points to location 0, 1, 1 is a point where the function starts. And now, by figuring out other points, you can trace the vector in space. So now this is 3, 0, 1/2. Let's say t equals to 5. If t equals to 5, r of 5 is the vector 75, -4, 1/6. So what is happening? In a three-dimensional system XYZ, you are going to find these points t equals 0, t equals 1, t equals 2, and you will be able to set some curve through those points. So vector value function allows you to trace any curve in the three-dimensional space. So guys, so far we only covered the straight line with those three parametric equations with x0, y0, z0. Now, any type of a curve, if you take a look at this power cord, that's not a straight line, right? That's not a straight line. And this could be a path of a fly or a mosquito or something, right? Through the, well, the butterflies fly this way. It's all over the place. So we can describe the flight of a butterfly, let's say, with this really curvy, bendy function here through the air. So you are going to have these vectors poking out. The vector r of 0, the vector r of 1. So this is the same as what you are used for your f of x, except now you're not getting a y value, you are getting a vector as the answer. So when you compute the vector valued function, vector is the answer, and if that vector is sitting at the origin, then it points towards a point, a location in space where the object is at t equals 0, if you want to think of t as time. Now, parametrization can be done in terms of arc length and other things, but it's easiest to understand if you have a time, and then obviously the line will be oriented because we know that the progression in time from t equals 0 to 1 to 2 to 3 will determine which way the object is moving, or the bug, or whatever. So now that we understand that the vector valued function is just a collection of functions in a row vector, and we understand that we can compute the values of the vector valued function by simply plugging in t and just computing the values. We also understand that it gives us vectors, that the vector, if it starts at the origin, will point to the terminal point, which is the location where the object is at that time. Now we can start thinking about some of the cool properties that we have. And one of these would first be to describe a circle. So if you have a circle in 2D, you can write a two-dimensional vector valued function for this r of t is equal to, let's call the radius over here lowercase a. So it's going to be a cosine t, a sine t. And we'll let t go from 0 to 2 pi to give me the full circle. So this is a vector valued function, which is just a collection of two parametric equations, and it creates a circle. Radius is a, and we know it's a counterclockwise because cosine was first. If you put sine first, it will be clockwise. So all of the features that we reviewed on the day one for parametric equations All of those features are still here. We're just writing it differently and calling it a name, which is vector valued function. If you end up with the ellipse that has A and B, major and minor radius, your R of t vector valued function would be A cosine t, comma B sine t. So if the values in front of cosine and sine are not the same, you get an ellipse. T is still stuck between 0 and 2 pi. T is still stuck between 0 and 2 pi. So now I have my circle. Oh, and the orientation is still counterclockwise because cosine is first and sine is second. Swap them, your orientation in the ellipse changes. So this is just another easy way to see that circle is just a special case of ellipse. Ellipse is the main shape, just like a rectangle is the main shape, and then circle is just when A is equal to B. The same like the square is a rectangle where A is equal to B, right? Rectangle has two different sides, but all of the features of the rectangle and the square, other than the length of sides, are there. They all have 4 sides. They all have 90 degrees in every corner, right? The adjacent sides are parallel. So all of these features are the same between the two, except this one has A and B, and this one has A and A. So for the circle and the ellipse, you get the same thing. Now, if you think about it a little bit over here, if your area is A squared and area is AB, and over here is A squared pi, what would be the area for ellipse? Should be common sense when you compare the 4 images and 4.
Would it be AB pi?
AB pi, exactly. AB pi. It's really, right, that's how math works. It has to make sense, it has to fit. Otherwise, anyway, that was a little side note. So we have perfect way, right, to describe all of these. Now let's say you have, for whatever reason, let's say you like pain and you just want to describe x squared, right, as the set of, as the vector valued function. Well, you can do that. It's okay. Because your good old y equal x squared, you can use what we call dummy variable here. So x equals t, and immediately y equals t squared. Because if you plug in t equals x, you get x squared. So now, your vector valued function r of t is, you list x first, which is just t, and then you list t squared. So t squared is just y equal x squared in a rectangular system. Exactly. So this is the two-dimensional realm. And now for three-dimensional realm, you're just adding the third component in the end over there. Now there are some really cool things that we can do in 3D, and one of those would be what is called a helix. So it's like a spring, right? It's a line. So you draw the helix and then draw the coordinate system. And if you look at the helix from the top view, in this case, what do you see? Yes, you get a circle. Beautiful. You get a circle when you take a look from the top. So xy is the floor on which the helix sits. Helix is just your spring, guys, right? So you take a look at the helix from the top, and all you see is a circle. So if I am to write the equation R for this, I have to start the x and the y components as a cosine t and b sine, a sine t. There we go. And now all I need to do is to take a look at the side. And let's say it's rising linearly, so we can just put a t over there. So this is the equation for the helix, which, right, it's just a spiral that goes up, which is a spring. So in the pool of the questions that I have for project, one of the questions that is applied question for you to measure and have fun with stuff is asking you to find a spring. I don't care if that spring is coming from your pen or you ripped it out of your car, right, from one of the shock absorbers, right? You just have a spring of some kind. And then you are supposed to give me the equation for that spring there are other aspects of that problem, but one aspect of that problem is to write the equation for that spring, which means you have to measure the spring on top, right, where it's the fattest, because it's a circle, and that's going to be that's the diameter. Half of that is the radius, which is your A, so you just have the first two already, and then you have to figure out what is the slope for t, right, to come up with a slope, because the spring can go like that, can go like this, right? So it depends on what slope you get. And then you can model it, right, in the computer. So then when you graph that, you see the same angles and you see the cell. So it's one of the, I have a whole bunch of these problems on a pile, and then just pick some of them and put them. Now, please note that these two over here are circle, and this is a Z wrap, okay? It wraps around the Z axis. I can make this wrap around T if I put, I can make this helix wrap around X axis if I put T in the X component, and then have sine and cosine on Y and Z component, right? So whatever axis it wraps around is where you're going to have this extra piece. Now, this extra piece doesn't have to be t. That's for a linear rise. You can have any other function in there. You can have t squared. You can have e to the t. E to the t would be terrible design for the spring, because it would make one circle like this and it would go whee, right? It will go right away, because exponential function rises very quickly, right? It goes actually like that. So you would start this, and then it will just go. It will go really fast up. So that's a terrible design with e to the t, but you can have it. Mathematically, it's okay. Now, the interesting thing is what happens if you put in a sine function instead of the t. You get Slinky. You know the thing that you can play like, actually, hold on. Think of a donut that it's actually, you take a spring and you connect it into a donut. So that's Slinky. And the kids, I have one in my office. There it is. So, Slinky. Cosine t, sine t, sine t. So cosine, sine, sine gives you Slinky, which is connected, right? So you can measure. So this is a lot of things that you learn in this class you can use to annoy people 24/7. Sometimes someone says, yeah, what do you know? I can calculate the equation of the spring you have in your pen. What do you know? See that? There's not going to be a comeback from that. Trust me, I used it so many times. Because I love people that say, what do you know? Or it's even better when they say, like, what do you know? I have kids. Really? There's a PhD in that? Nice. All right. So, Slinky. Curve given by R A cosine t, A sine t, A sine t. Now, obviously, you can make this into ellipses and all of that just by putting A, B, C, A, B, A, B, or A, B, B, or whatever. Just come up with whatever you want. You can make it into an ellipse in any of the cross sections. That's terrible, but that's what it is. All right. And they talk about limits and continuity for these things, which is part of the calculus, so I'm just going to stick that in the next section. Your homework will have a whole bunch of these problems that have a blue T on it, which means use the technology. They say 15 through 26, graphing curves. And they give you a whole bunch of these circles to graph, which is interesting, and then a whole bunch of helixes. There we go. And then all of a sudden they start asking you for 23 to 26, and then all of the problems 27 to 30 under exotic curves to graph all of these other, which you will just plug into the software, and it will give you the graph. Some of the cool questions to consider are where they ask you to match the equation to the curve given. And that is, those are some of the most interesting problems, in my never humble opinion. And I think they have a mistake. Oh, no, they don't. Okay. I'm just trying to see if there is any way because I can display all of these at once and you can't see them. If I try to draw these, it will be disastrous. But okay, let's try and do these match problems, and then I'll see. So capital A. I'm going to regret this really fast. Okay, that's the shape. Z-axis cuts through here. X and Y axis cut through there. So that's that shape. Then we have B. B is going to be X, Z, Y, and it seems that it's wrapping around Y. C is going to wrap around X, so we'll draw like this. And then just have it go like that. D is a line like it's like a parabola like this. E is a straight line through the origin. And finally, F will be the circle which levitates above the plane. Great. And now we're going to have 6 equations, and each one of equations at vector valued functions will connect to one of these. So lowercase a is t negative t t, lowercase b t squared t t, and then we'll just put the match next to it. Lowercase c 4 cosine t 4 sine t2, d 2t sine t cosine t. So these are all spiky brackets because they're vectors. E, lowercase e, sine t cosine t sine 2t. And finally, lowercase f, sine t 2t cosine t. Great. Now, out of these 6 equations that you see here, you should know immediately 3 of them, what they are. You should know CDF. So what are D and F? We just talked about it. Springs, great. Helix, now these wrapping around which axis? X-axis. So which one wraps around X-axis? B. Capital B wrapped. Oh no, wait. Oh no. I mislabeled it here. C. Capital C wraps around X-axis. Okay. So capital C. So D capital lowercase d, capital C. Great. What's happening with F? Wraps around Y. So that's B. $4 million. What's happening with C? So that's capital F. Very good. C is capital F. Note that the Z component is just a number. So it's just the elevation at which this circle is. You need some kind of a function on that Z in order for it to progress in a Z dimension, right? In a Z way. But the Z is constant. Z is always 2. No matter what your X and Y do, Z must be 2. And the only one that has a flat Z is F. All others have variation in Z, going up and down. Z axis is constant only with F. So now we eliminated all of those. So the next order of business is to figure out, well, it's easy to spot that capital E. What is capital E? The line.
That's gotta be A.
There has to be lowercase a, because lowercase a has no squares or anything like that. You see a t, a negative t, and a t. So they're all linear. So this must be E.
D would be D because so it's parabola.
Excellent. D is the parabola. So D being the parabola is going to give us D. And now by process of elimination, this monstrosity over here is capital A. And look what it has. It doesn't have, right? First of all, we see sine, cosine, sine. We know that's a Slinky. Now this one is sine 2t, so it's just going to change the shape of it a little bit, but it's still going to maintain the main feature, and that is that it loops back and connects to itself. Remember what the trigonometric functions, what they do? They're periodic. They keep repeating their state over and over and over again. When you have a sine and cosine describe a circle, it's a closed line, right? Other ones, they don't loop back to connect for straight lines or parabolas or anything like that. They don't go looping back and connecting to itself. Now consider helix. Helix, when you look at it one way, it's connected because it's a circle that it's connected. But when you look at it the other way, right, from the side, it kind of goes up and never ends. So you have to have both of those features present in equations as well. When you look at equations as a sine cosine pair, where those are the functions that are periodic, they loop back and they create circles. But then you have the feature of it, which is a feature of a t, which could be, or whatever, t squared or e to the t. That's a feature that doesn't loop back and connects to itself, which is why the helix will go on. Now Slinky, cosine, sine, sine, or whatever combination you get, is something that loops back and connects. So the picture here for A loops back and connects. It's not a busy Slinky like we've seen at the lecture, but it's, you know, definitely something that you can make quickly with the rubber band or something. So these are you know, just a few ways in which you can observe these lines and then try to reason what they actually are. The more of these you graph in the software, the better off you'll be in terms of recognizing what needs to change in order for the line to change and so on. So just practice this as much as you can. Use the graphing utility as much as possible to see what these curves are. And then when you have a curve, change some qualities of the curve. Because if you take a look at lowercase a, lowercase b, they are the same apart from one square, right? And one produces parabola, the other one produces straight line. And then you say, oh yes, of course, all linear has to make linear line. And if I have a quadratic somewhere, it's going to make. Now, what happens if you have another t squared? What happens if all three are t squares, right? So these are the things that you guys should try on your own and see what you get. So that's this. We'll take a few minutes off, and when we come back, another very short section, which is calculus of vector valued functions, and then we'll move into the lab portion of the day. Bye.